Yeah, welcome. The topic we'll be discussing in this lecture is clusters. So if you recall from the beginning, whatever we have discussed, mm, uh, so the we have discussed with the classification, right? How the what are the ways in which the processors were organized. So if you recall this diagram here, if you see the processor organized as, yeah, this is Flint's taxonomy: SISD, SIMD, MISD, and MIMD. Under MIMD, we have two categories: shared memory and distributed memory. Under shared memory, the commonly used is SMP, symmetric multiprocessor, which we have discussed already. The one which is coming under distributed memory or loosely coupled system is clusters. Okay, so that's what we are going to discuss in this lecture. So we are going to discuss about clusters, right? Okay, fine. So basically we are discussing about parallel processing. So cluster also provides one type of parallel processing. It is an alternate to SMP, symmetric multiprocessor system. In a symmetric multiprocessor system, there will be shared memory, whereas in clusters there will be distributed memory. Now, how will we define cluster? See, a cluster is a collection of several individual computers. A cluster is a collection of several individual computers. You can assume that there are many individual computers. Okay, so maybe hundreds of individual computers are there, and these individual computers will 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 put together as one collection or one set. Okay, and to the user will feel as if this is one single machine. User will not be able to differentiate like whether it is one machine or it is a group of machine. Actually, it is a group of machine. Everything is an individual standalone computer, but this individual standalone computer, they uh, they form a group. We group them together, and they provide an illusion to the user as if it is a single machine. Okay, so this single machine will be equivalent to a powerful symmetric multiprocessor. Okay, in a symmetric multiprocessor, what happens inside one system, that system will occupy a big room. Inside one system there will be hundreds of processors. Okay, there will be lot of IO devices connected, but everything, it is actually one system. But in cluster, that is not the case. You will have individual computers. These are standalone computers. Every computer will have its own IO devices, memory, hard disk, etc. But we will form them as a group, and they will work together, and it will provide an illusion to the user as if it is a single machine. Okay, so it is defined something like this: a cluster is a group of interconnected whole computers. Whole computers means standalone computers. By individually they can work. Okay, these computers will be working together as a unified computing resource. Okay, that is, it will be unified means it will, for the user, the user will feel as if something like a single unit. Okay, that can create an illusion of being one machine. Okay, for, with respect to the user, it will be something like a single machine only. Okay, so this is how clusters were defined. Whole computer means a system that can run on its own. So that is how whole computer is defined. It is something like a standalone computer. So the clusters are effective in terms of client server applications. So one of the system in the cluster will act as a server, and it can serve the client's request. So the clients will be something outside the server, outside the cluster, and the server will be placed, and the clients will be placing the request, and that can be satisfied by the server. Each computer in the cluster is called as a node. So there are several computers in the cluster. They form a group and they work together and provide an illusion as if being a single machine. But there are multiple computers. Each of these computers are called as a node. So the benefits of clusters are absolute scalability. Absolute scalability means the number of devices, the number of computers that will be grouped together to form a cluster, there is no limit on that. You can keep 10 computers and form a cluster, or you can keep hundreds of computers and form a cluster, or you can keep thousands of computers and form a cluster. It is absolutely up to the individual's requirement. Or if you want to have a cluster which is equivalent to that of a symmetric multiprocessing system, and that symmetric multiprocessing system has 100 processors or 100 memory locations, in that case, I mean, symmetric multiprocessor has common memory location, 100 processors and 100 IO devices. In that case, you may connect 100 devices, 100 standalone computers or whole computers, and you may form a cluster. So that is called as absolute scalability. Absolute scalability means whatever you want, the performance which is equivalent to a standalone supercomputer or a standalone parallel computer, that performance we can get in a cluster machine with with appropriate number of nodes. So that is what is called as absolute scalability. So depending on our requirement, we can fix the number of nodes. That is what is called as absolute scalability. And the next is incremental scalability. Incremental scalability means it is like initially I don't want to go for many number of nodes. I will start with 5 nodes or 10 nodes. Then depending on the performance or depending on the profit, I shall increment the nodes. From 10 nodes, I will make it 25 nodes, then to 50 nodes. So cluster supports that option also. So that is what is called as incremental scalability. So the difference between absolute scalability and incremental scalability is absolute scalability means at a stretch, if you want to build a cluster which is equivalent to a supercomputer, you can do that. You have to make some calculation like how many nodes should be there, all those things, and accordingly you can set up. And otherwise you may also go for incremental scalability. No, I don't want to invest that much initially. I will start with a modest setup, and then depending on the performance and other factors, I will improve. So that kind of facility also clusters provide. That is what is called as incremental scalability. High availability. High availability means there are many nodes in the cluster. The cluster is a collection of nodes. So there are many nodes. If one of the node fails, that is not going to affect the system. That is not going to affect the system. In fact, the user will not even feel that something has gone wrong. So that is what is called as high availability. Superior price or performance. If we compare the price or performance of a cluster with SMP, then actually the price or performance of clusters are better than SMP. For example, if there is an SMP with 100 processor and 100 IO devices, and you are using cluster with 100 computers, the cost of the cluster, the cost of these 100 computers will be less than one SMP with 100 processors. So that is what, so it is superior in price. And coming to performance, the performance of these clusters will be better than SMP, because here every machine is a standalone computer. It is not just a processor alone. So it is superior with price and performance when compared with SMP. So there are several ways of configuring clusters. So here is 2 examples per given with just only 2 nodes. This is one node, this is another node. Again, in a cluster also, each machine can have multiple processors. Here if you see, this node has 2 processors, and it has one memory and 2 IO modules, and these this processor, this computer, this node also has 2 processor, two IO modules and one memory, and each of them have their own disk. This is the hard disk. Each of the node has its own disks, and these two computers were connected through a high speed link, which can be either a LAN or a WAN, and through that they communicate, and they collaborate, and they work as a unified machine. That is, they provide an illusion to the user as if it is a single machine. This is one setup. This is another setup. Here almost everything is same, apart from here one more thing is added, which is called as RAID. RAID stands for redundant array of inexpensive disks, or redundant array of independent disks. I can be either for independent or inexpensive. I think we learned this in operating system also. As per operating system, it is redundant array of independent disks. So here, apart from the individual disks that is shared with individual node, there is also shared disk. These shared disks are nothing but RAID, redundant array of inexpensive disks. So there is a redundant array of inexpensive disks which are shared by both the nodes. Okay, or any number of nodes which are in the clusters, they may share this common disk. So they can they can frequently copy their data here, so that if one of the machine fails, then the other machine can take over. So that is the main objective of cluster. Why we have so many machines? Out of all these machines, only one machine will act as a server. So if some machine fails, then other machine should take over its job. So here the purpose of providing this RAID disk is so that the data will be available at a common place, so that if some of the node is not available, still the data will be available through some other node, because another node may be also will have the access to this same RAID. So there are different ways in which the clusters can be organized. The first method is called as passive standby. Passive standby means, so generally we should make one understanding that so a cluster has many machines, it has many computers or many nodes. Out of that, one of the computer will act as a server. Only one of the computer will act as a server. Say this is the server. Now if any request comes from outside, that is from outside world sees this entire thing as one computer, so they gave a request, but actually the request will go to the server, and server will service that request. Okay, with this scenario, let us understand what are the different ways of organizing clusters. So the first method is passive standby. This technique, what it says in the sense, so there is a server, so all the request comes to the server, and server should satisfy all the requests. So suppose if server gone down, suppose if server got crashed, then what will happen? So we always maintain a system in a standby mode, and this system is called as passive standby. That system will not do anything. It will just it is a standby system. It is a standby system, but it is a powerful system. It has capability equivalent to that of a server, but it won't do anything. It will just keep on waiting till the server fails. If server fails, then it will take over the role of the server. So here is the description. There will be a secondary server that takes over in case of the primary server fails. If the primary server fails, then the secondary server will take over. The advantage of this model is it is easy to implement, but the limitation is the cost is very high, because the secondary server is unavailable for other processing tasks, or you can say that the secondary server is not fully utilized. We are not at all utilizing. During other time also you may utilize it apart from acting as a standby. So that is one of the drawback. And so how the secondary server recognizes that the server fails, in the sense, normally the server will keep on, at every frequent intervals, the server will send some signal to the secondary server. This signal is called as this signal is called as uh, heartbeat signal. Okay, at frequent intervals, the server will send a signal to the secondary server, the standby server. This signal is called as heartbeat signal. Say every 50 milliseconds, once it will send the heartbeat signal. So if the secondary server does not receive heartbeat signal for continuously 100 milliseconds or 200 milliseconds, then the secondary server will understand that server has failed, and then it will start playing the role of the server. So this is how this concept works. But actually this is not a very attractive technique, because we are not effectively utilizing the standalone server, and also this cannot be even called as a clustering method, because in clustering method there should be more than one system. At least there should be minimum two nodes. Here if you have only one server and the other one is only in the standby mode, then you cannot call it as a clustering method. So the second method is active secondary. So in the first case we discussed passive standby. The second method is active secondary. Here the secondary server is also used for processing tasks. Apart from taking over the primary server when the primary server fails, the secondary server will also be used for processing the tasks. The advantage is reduced cost, because secondary server can be used for processing. So now we are utilizing the server effectively. The disadvantage is increased complexity. So the complexity of the model will increase, because now we have to manage two servers, and which request should be processed by which server. All these things should be decided. So this active secondary can be classified into three categories. One is called as separate servers, the other one is called as servers connected to disks, and the other one is called as server share disks. Okay, this second method is also called as no share. The second method is also called as server connected to disk. It is also called as no share. They don't share anything. We'll discuss. So the first one is active secondary. The first one is separate servers, which means that so there will be two servers, one active server, one secondary server. Each of the server will have their own disks. Each of the server will have their own disks. Data is continuously copied from primary to the secondary server. So primary server will have its own disk. Secondary server also will have its own disks. Data will be continuously copied from primary server to secondary server. Say for every half an hour or for every 1 hour, the data from the primary server will be copied to the secondary server, so that if primary server fails, then secondary server can function with full resource as like the primary server. The advantage is high availability. The disadvantage is there is a overburden on the network and on the server, because you are always saying that the primary server should copy everything to the secondary server. So always there will be the network will be overloaded, and server also will be overloaded due to continuous copying operation. So this is what is called as separate servers under active secondary. Then the next method is servers connected to disks. This is also called as no share. This is also called as no share. Here what happens in the sense, there will be, again we'll have two servers. Servers are cabled to same disks, but each server also will have their own disks. If one server fails, its disks are taken over by other server. So this is similar to something like this. This is similar to this second model. What we are discussing, server connected to common disks. That's what we are discussing. Server connected to disks, but each server is cabled to same disk, but each server also have its own disks. If one server fails, its disks are taken over by other server. As long as the server does not fail, it won't be taken over. So that this technique is called as no share. So this is only connected. It is only connected, but there is no sharing. these terms you should understand clearly. Two servers, both the servers are cabled to the same disk. Cable means they are just connected, but they are not sharing anything. Each server will also have its own disks. If one of the server fails, then the other server will take over the first server. So here you can see this, it is nothing but this model. The servers are cabled to the same disks. That is nothing but RAID. But each server has its own disks. This server has its own disks. This server has its own disks. Okay. In this RAID, there may be some partition. Like you may call it as volume 1. Volume 1 will be used only by, say, server 1. And there may be another partition called volume 2. Volume 2 will be used only by server 2. But there is this memory is cabled between both the servers, but it is again partitioned like volume 1 and volume 2. Volume 1 will be used only by server 1 and volume 2 will be used only by server 2. Suppose if server 2 fails, then server 1 will play the role of the server 2. At that time it will take over volume 2. At that time there will be some mechanism it has to go through by which it can get access to volume 2. Otherwise it won't have access to volume 2. So that is why it is called as no share. They are just cabled to the common disk, but it is not shared. Normally it is not shared. V1 and V2 are not shared, but if one of the server fails, then the other one can get the access to the other volume. So the benefit of this model is it reduces network and server overhead due to elimination of copying. Here we need not copy. Each server will just copy only to their volume. Server 1 will copy to volume 1. Server 2 will copy to only volume 2. Only when somebody fails, no, then they will get the access to other volume. So the limitation of this method is to implement this method also we need a RAID disk. That is, we need a redundant array of inexpensive disk. And the other model of active secondary is server share disks. Here actually they share the disk. Not only they are connected, but they share the common disk. Multiple server simultaneously share access to disks. Simultaneously they can access the same disk. So the benefit is low network and server overhead. Here it is reduced network and server overhead. Here it is very low network and server overhead. And also reduced risk of downtime caused by disk failure. So disk failure or downtime, all these will be reduced. Reduced risk of downtime caused by disk failure. The probability of downtime due to disk failure is very, very low. The disadvantage of this model is here also we say that multiple servers can simultaneously access the disk. Yes, it means that both the server has access to this full disk. Anybody can access anything. It means both of the servers, server 1 can also access any part of the RAID disk. Server 2 can also access any part of the RAID disk. Okay, they have both of them as access. Okay, but that doesn't mean that both of them can access at the same time. Okay, the definition we told simultaneous access. Simultaneous access in the sense both of them has the right to access. Both of them has the right to access, but they cannot access at the same time. There will be some lock mechanism. So this is something like a shared resource. This is in operating system we have learned. A shared resource can be accessed by only one process at a time, not more than one process. So in that case we need some lock mechanism. So there should be some lock mechanism. If server 1 want to use, first it should check whether it is locked or not. If it is not locked, then server 1 will use it. When server 1 is using it, this will be locked. Now if server 2 checks, it is already locked. So server 2 has to wait until the lock is released. Once the lock is released, then server 2 can access. So this is how servers with shared disks work. Here multiple servers has the right to access simultaneously, but that doesn't mean they will access. They should not access simultaneously because it is a shared resource. It is a critical section. Only one person can access it at a time. So it has low network and server overhead. It has reduced risks and downtime. The limitation is it requires a log manager software. Okay, usually used with disk mirroring or RAID technology. So there should be some option available to lock the RAID disk such a way that only one person, one server can use it at a time. So these are the broadly how the clustering is done. So broadly it is classified as passive standby and active standby. Under active secondary, under active secondary we discussed these three cases. Then we'll be discussing the operating system design issues with respect to clustering. Generally, there are two types of operating system followed with clustering systems. One is called as high available cluster. The other one is called as fault tolerant clusters. So the difference between high available clusters and fault tolerant clusters are, in case of high available clusters, the clusters will be available as much as possible. Okay, so so that is the clusters offer a high probability that all resources will be in service. If a failure occurs, but in case of a high available clusters, so it tries to provide maximum availability, but say due to some reason there is a failure. So it is a client server model. That is, the clusters in the cluster there will be a server. Client are placing the request. So say the client is placing one request and that request is partially processed by the server. Meanwhile, the server failed. Now what will happen? Now obviously the secondary server will take over. But secondary server, for taking over also it may take some time, right? At least it may take some milliseconds or seconds or whatever it may be. Some time it will take. Now the whatever the instructions that were, whatever the requests that were partially processed by the server, that will be lost. This new server, the secondary server, will not mind about that. So that will not be taken care by the secondary server. But say that some client has requested something previously, and that request while processing partially, the server has gone down, so the secondary server has taken over. Now the secondary server will not be knowing about the instructions or requests that were partially processed, so that is gone. But say the client is once again placing the same request. Previously the client has placed some request, and when that request was partially processed, the server gone down. So now the secondary server is taking over. Now the client does not got any response for its previous request. So the client may understand that okay, something has gone wrong, or after a certain period of time client may place another request. Okay, another request means it's a copy of the previous request. Okay, if it is a copy of the previous request, now this server may process this request. Now this server will process this request. Okay, but by the secondary server by itself will not try to understand like what are the transactions which are partially executed when the server got crashed, and how to recover that. All those things secondary server will not do anything by itself. But if the client requires the same tasks again, of course the secondary server will do that. So this type of model is called as high available clusters. Okay, so they are available as much as possible, but only during that time it is not available. That is the request the client gives when the server is getting crashed. So such request will be partially processed, and the secondary server which is taking over will not take any steps to recover such partially executed instructions. But only thing that can be done is if the client asks the same request again, then the secondary server will satisfy that request. Okay, the second model is a fault tolerant model. Actually the fault tolerant model, it ensures availability of resources at all time. It ensures resource availability at all time. This is high availability. High availability to maximum available, that's all. But 90% available or 95% available. But fault tolerant, it ensures that data will be, or the resources will be available at all time, irrespective of anything may happen. The server may fail, or the server may fail when a transaction is executed partially, whatever it may be the reason. But fault tolerant systems guarantee that the resources will be available always. Okay, so how it achieves that? So basically it ensures that resources will be available always, resource availability for all time. Okay, how it ensures that? How it ensures that in the sense, actually it maintains uh, something called as, just a minute. So so it ensures resource availability for all times. So that is what the special feature of fault tolerant system. How it ensures in the sense this is achieved by using redundant shared disks. This is achieved by using redundant shared disks. That is, the primary server and the secondary server will share the same disk. Okay, something like a RAID disk. So this is a RAID disk. The primary server and secondary server will share the same disk. So all the request that is coming to the primary server, say this is primary server, this is secondary server, all the request that is coming to the primary server will go to the RAID. So the client is giving one instruction, one request, while partially processing, the server has failed. Now that data also will be available in this shared disk. That data also will be available in the shared disk. Okay, and also it in the shared disk it maintains two types of transactions. In the shared disk it maintains two types of transaction. One is called as committed transactions. Committed transaction means the transaction which are completed fully. So these are called as committed transaction. Okay, in database you might have learned commit. Commit means if a transaction is completed, it will be committed. It means it is saved. So it maintains two types of transaction. One is committed transactions and the other one is uncommitted transactions. Uncommitted transaction refers to the partially processed request. Okay, this uncommitted transaction refer to the partially processed request. So at every millisecond or every nanosecond, it writes the data to the common disk. So for every request, it will specify whether it is committed or uncommitted. Committed means that request was fully processed. Uncommitted means it is partially processed. Okay, now say for example a client is placing a request, but meanwhile while processing the request partially, the server fails. Now the secondary server will take over. Now after taking over, secondary server will check this RAID, which transactions are uncommitted. So by seeing that, secondary server will understand that okay, these transactions are uncommitted, which means they are partially executed, and it will start executing that. Okay, so this is how this fault tolerant system ensures resource availability at all times. Okay, right. So again, this resource availability thing can be thought of as two styles. One is called as failover, the other one is called as failback. Failover means the function of switching applications and data resources from the failed system to an alternative system is called as failover. Okay, so if the primary server fails, then the secondary server will take over. So secondary server takeovers means what? Previously, whatever the application and the data that were handled by the primary server, now it should be given to the secondary server. So that process of handing over the applications that is connected with the primary server now should be given to the secondary server. The data that were connected to the data resources that were connected to the primary server, now that should be given to the secondary server. This process is called as failover. Handing over the application and data resource from primary server to secondary server is called as failover. Whereas failback, what does it failed back means? After some times this primary server may recover. Say after 1 hour or 2 hour or after 1 day or 2 days, this primary server will recover. Once the primary server recovers, again these applications and data resources should be given back to the primary server. This is called as failback. This is called as failback. Okay. Failover means handing over the application and data to the secondary server from primary server. That is called as failover. But later the primary server may come back again. It may recover. So then once again the applications and data resources should be given back to that. That is what is called as failback. Okay, right. So this is how the operating systems design issues were handled for clusters, and the operating system should ensure increased scalability. Okay, it should include new computing in scheduling. Incremental scalability, we have already discussed. That means we should be able to, initially we may be starting with a small number of devices in the computers in the cluster. Then we should be able to gradually increase the number of computers, and when a new computer is added, automatically it should be included in all activities. Okay, and middleware should recognize the process. That process may switch between the processes may switch between machines. The middleware should understand that it is not that only one process is going to only one server is going to deal everything. Suppose if the server fails, then it should be handled by some other server. So the middleware should understand all these things. Okay. So how the parallel computation can be achieved through softwares, through operating system. So we are discussing all these comes under operating system design issues of clusters. So there are three approaches to handle parallel processing in with software, that is with operating system. One is with parallelizing compiler. That is, the compiler should decide like which part of the instructions can be executed parallelly. Okay, parallel execution means some instructions may be executed by more than one client at the same time in a given application. Not every instructions you can execute like that. So the compiler should recognize which part of the code can be executed parallelly, and these are then split off to be assigned to different computers in the cluster. Okay, because different computers will run these at the same time. But it is not that easy to define such a compiler. It's a bit difficult. The next is parallelized applications. In this case, it is not the job of the compiler. Rather, it is the job of the application. While writing the application itself, the programmer is aware that this program may run in the cluster model. So accordingly, the programmer will write the program, assuming that in a cluster network how it should work. So by default, the program has the ability to work in a cluster environment. That is what is called as parallelized application. The third is a parametric computing. So in some applications we may want to execute a certain algorithm or a certain code repeatedly for several number of times with different parameters. Example, for simulation. So in case of simulation, the application may be same, but different times you may run with different parameters. In such case, this parametric computing can be used. So these are the different ways of parallelizing through operating system or through software. So this is the cluster computer architecture. Here you can see all these are individual standalone computers. Okay, this is a computer. Everything is a separate PC or a computer, and all these computers are connected to a high-speed network or switch. And on top of this, there is a cluster middleware. This cluster middleware provides the single system image to the user. Okay, and on top of this cluster image, we have applications, and we have the parallel programming environment and parallel applications. Okay, so this diagram shows the architecture of the cluster computer, and this is another architecture with what you call, this is a cluster configuration with blade servers. So what is a blade server? So blade servers are type of servers. These are a type of servers. Basically uh, they are used in data centers. Basically these blade servers are used in data centers. Okay, so data centers, you may ask, like, what is a data center? Data center is something like a huge building which is dedicated only for computers. There may not be any humans there. Okay, they are dedicated only for computers, and you can see here actually all these are computers. This is one rack. This is one rack. This one rack contains so many computers. This is one computer. It will have a processor, memory, IO device, disks, everything. This is one computer. This is one computer. Okay. These computers may not look like our normal computer, but actually these are computers. So this one rack contains, this houses several computers. So these are called as actually blade servers. These are called as massive blade servers. Okay. So each one, so here you can see each of them, there are several such racks, and in each of the rack there are several computers. Okay, these are called as blade servers, and each of the blade server will, so all they are connected through network, through switches and other things. Each of the blade server can operate, I mean, can communicate information to the network at the rate of 10 gigabits per second or 40 gigabits per second. Okay, but these switches can provide high speed connectivity. They are connected at the rate of 100 gigabits per second. Okay, right? So this is one of the common implementation of cluster. It is through blade server. Okay, so this is also a server architecture. It houses multiple server modules, and these are called as blades in a single chassis. This is one chassis. In one chassis, it has many server modules. Okay, so they are like a standalone computer. Each blade. So every computer is called as a blade. This is one blade. This is another blade. Okay, every computer is called as a blade. Each blade will have its own processor, memory, and hard disks. Okay, and each blade will offer a, it can communicate with other blades with a data rate of 10 gigabits per second or 40 gigabits per second, and the switches communicate at the rate of 100 gigabits per second. If you compare cluster with SMP, everything has its, both has its own advantage and disadvantage. SMP is actually easy to manage and configure, because even though it has 100 processors or many IO devices, it is finally it is only one single unit. Okay, but cluster, there are multiple devices. Okay, but cluster is far superior in terms of incremental and absolute scalability. Okay, here scalability is very tough. If you want to scale, you have to add processor, then you have to think whether you have sufficient space or not, all those things. Okay, SMP, it is much closer to the original single processor model. See, in a single processor model, we have one processor, one memory, and few IO devices. In SMP, we have 50 processor, many IO devices, etc. So it is similar to the normal PC architecture, uh, with a, what you call, uh, with more number of devices. Okay. Mm, so I mean, we can, already we have the knowledge of dealing with a single computer, so that knowledge can be transferred here, but that is not the case with clustering. Clustering, it is totally a different concept. We are going to use individual machines and we are going to make it work like a unified one, but it is superior in terms of availability. And SMP actually, it requires less space and lower power consumption when compared to clustering. Actually, clusters needs more space, and also they consume lot of power. For example, these blade servers and all consumes lot of power. Okay, but in clustering, all components of the system can be readily be made highly redundant. You can have multiple copies of everything. Another advantage of SMP is well established and stable. Clustering is relatively a new concept compared with SMP. So it may take time for clustering to become established and stable. But nowadays we can assume clustering is more stable, because if you see this, see Google, Microsoft, all these things, all they maintain their content in the data servers, in the data centers. So this is one data center. Okay. Google, Microsoft, Yahoo, okay, Apple, they maintain their data where? Everything in the data center only. So does Google server fails anytime? No. So why? Why it is not failing? There may be redundant copies. There may be redundant copies. Okay. It might have been stored in multiple blades. Okay. So that's the reason. So that's it about clustering. So we'll stop here. Thank you.